Japan is renowned for its natural beauty. It's home to 26 World Heritage Sites, including the incredible bamboo forests and the world-famous Mount Fuji. But beyond its idyllic lakes and beautiful cherry blossom season, this country's also become a world leader in another area: engineering. And I've had the immense honour of being able to visit so many of Japan's incredible construction projects. But one of them truly stands out above the rest: the incredible mega plan to disaster-proof Tokyo, the world's biggest city, against 5 massive threats for the next 100 years.
Inside the shaft from this here.
Yep.
This is amazing. It's huge, huge space carved out in the earth. People created this, and they're doing it for a project that's going to change the lives and impact millions of people. Best industry in the world. Welcome to Tokyo. This is one of the most incredible cities on Earth. The bullet train was shooting through here back when other countries were still using steam locomotives. This place was an electronics powerhouse when Steve Jobs was still working out of his garage. And it kind of knows a thing or two about building big. This place is so big, so sprawling, so huge, so well organised that it's like you're in some kind of bubble. You feel like the place is indestructible. But look a little closer and you realise there's something very different about Tokyo.
We have breaking news.
7.1 magnitude earthquake.
Wind, flood, landslide warning.
This city is constantly on the brink of disaster. Earthquakes.
Magnitude 5.7 earthquake was felt throughout Tokyo.
Volcanoes.
Mount Fuji is one of
Volcanic ash could cripple the Tokyo area.
Floods.
The disaster is far from over for
impacts
residents.
on the Tokyo area.
This is a city that really shouldn't be here, but it is because engineers have developed some of the most extensive and advanced countermeasures anywhere in the world. But it's not enough. The number of threats Tokyo faces and the damage those threats could cause is only getting worse. A quarter of Japan's population now lives in the greater Tokyo area, and the city centre accounts for more than 20% of this country's GDP. If disaster struck now, it wouldn't just be bad for Tokyo. It would have a knock-on effect for this entire country and even the world. This place, this city, really matters. But Tokyo is not exactly a city that does things by half measures. So when it came to protecting itself from annihilation, it decided to go big by building one of the biggest civic defence projects in history. I cannot describe the feeling of coming down those stairs. This is amazing. How much water are they expecting to flow through here?
This is a machine to simulate earthquake in the laboratory.
I am currently 5 stories beneath the streets of Tokyo. The goal is to achieve nothing less than total protection from everything the world can throw at it for an entire century. This is the $100 billion plan to save Tokyo. I'm so excited for this. On my way to see one of the most iconic buildings in Tokyo, the Tokyo Skytree. It's incredible. It was completed in 2012. The first thing you notice is it's covered in this amazing lattice structure, and that's designed to help it withstand a magnitude 7 earthquake. It's only when you get up high like this that you get a sheer sense of the scale of Tokyo. It spreads out for miles in every direction. But what you also realize when you come up high is how flat the city is. You can sort of see down there through the clouds if the weather was better. This is a really big flat area. Now, because Japan is covered in mountains, cities tend to get constructed on big, large, flat plains like this. But that also makes them sitting ducks for pretty much every natural disaster you can think of.
This is the Pacific Ring of Fire, a 40,000-kilometre tectonic belt. It was this that forced Japan out of the sea in the first place, but also left it studded with volcanoes, 111 of which are still active today. And while you only need 2 plates to grind together to create some seismic activity, Japan lies across 4. Which means this one country is struck by 18% of all the world's earthquakes. And as if all that wasn't enough, thousands of kilometres of ocean to the south leaves it wide open to typhoons and tsunamis rolling in from the Pacific. Throughout its history, Tokyo has been quite literally razed to the ground numerous times. But now, with 40 million people living here, that simply can't happen again. Which is why, in December 2022, the city's government hatched a plan. The Tokyo Resilience Project.
Okay, now you're going to have to keep up because this is by far the biggest infrastructure project we've ever covered. Launched back in December 22, it's going to take 18 years to fully complete and cost 17 trillion yen, which is around 109 billion US dollars. This really isn't the case of a new floodgate here or a bit of earthquake proofing there. It's a meticulously planned project to protect every part of this city from disaster. There's no structure too big, no detail too small. What does that look like? Well, it means developing soft infrastructure like establishing evacuation routes and improving response times, but also building some truly epic infrastructure like tunnels. Massive tunnels!
Or widening rivers.
324 kilometers of rivers. There's so much involved because this isn't just about protecting Tokyo from one threat like a tsunami. The TRP has identified no fewer than 5 threats that could bring this city to its knees.
It might be a national symbol, but Mount Fuji also happens to be an active volcano that could blow at any moment. But even if it smothers downtown Tokyo in ash, the city is going to be cleaned up and running again in no time thanks to meticulously planned clearance routes. For those living on nearby islands, new evacuation points are being established to whisk residents away to safety on specially chartered ships.
We all remember the pandemic. Now, in a place as densely populated as Tokyo, any kind of disease outbreak is taken incredibly seriously. And one of the measures the city is now taking to try and prevent against that is the creation of more than 2 kilometres of new parks.
Extensive cycling routes are being created, as well as riverside walkways to give people an alternative to crowded public transport.
Don't you hate it when you can't get a signal? Well, now imagine the disaster struck, the phones are down, and there's a blackout. Well, come 2040, that just won't happen here, because the city's building a new power and communications grid that's going to ensure that Tokyo never loses connectivity and never experiences a power blackout.
That means reinforcing undersea cables, building new satellite capabilities for the city, and providing cloud storage for businesses so they're always connected. And that's just scratching the surface on the measures being taken to protect the city from 3 potentially devastating threats. But all of that pales into comparison next to the last 2 mega threats facing this city.
I've come to NIED, which is Japan's National Research Institute for Environmental Hazards and Disasters. I'm here to see all kinds of fascinating experiments, but this is also the site where they have the early monitoring system for earthquakes called MOLAS.
Set up in the aftermath of the 1995 Kobe earthquake, this is a nationwide observation network for earthquakes, tsunamis and volcanoes. Seismic activity is monitored in real time using a network of 2,000 seismometers positioned right across Japan and the surrounding ocean floor. When a disaster strikes, it's going to be detected here first.
The main control room for MOLAS is so secret and so secure that we're not actually allowed inside it. But what you can see here on this map, this representation, is where these LED dots are, just how extensive that network of seismometers and sensors is. This is actually slightly out of date. There are now more on the land and more in the waters around Japan as well. And what stands out to you is this plain here, which I mentioned earlier, that big flat plain where Tokyo has grown up and been established. And if you look just south of Tokyo, out into the sea, you see there's a collection of islands.
Two of these islands, Izurushima and Miyake, have erupted 7 times in the last 100 years. And work's underway to establish a permanent evacuation infrastructure for when it happens again.
Volcanoes are going to be around forever. They're kind of a fact of life when living on planet Earth. And they're chaotic, they're difficult to predict. There's one other danger which is much more predictable, which has researchers very worried, because the threat of it is only getting worse.
It might not seem like it from the endless expanse of concrete, but Tokyo is a city shaped by water. It's part of the reason the capital was moved here from Kyoto. More than 100 rivers and canals flow through here, with the city dominated by the enormous spiralling moats around the Imperial Palace. But like so much else here, what actually helped this city to thrive is also its Achilles heel.
As massive amounts of rain continue to drench Tokyo, millions of people have been ordered to evacuate. At least 4 people have died and dozens more hurt.
Flooding is a critical threat to Tokyo. 124 square kilometers, a fifth of central Tokyo, lies below sea level. So the TRP is not taking any chances. Seawalls are being raised in case of a 60 centimeter sea level rise by 2100. That's more than twice as much that they've risen since 1880.
But that's not all. Tokyo faces thousands of miles of Pacific Ocean to the south, and the current from that brings a steady stream of typhoons that dumps torrential rain on the city.
Now, that's nothing new, but because of the urban heat island effect and climate change, Tokyo's climate is becoming increasingly subtropical. That means storms are getting more frequent and more severe. Over the last 40 years, the amount of heavy downfalls have almost doubled in Japan. Flooding was a daily part of life in Tokyo, and it was only getting worse. In 1992, the city's government embarked on an extraordinary project in response to this challenge. An underground system made up of 5 silos which collect floodwater from nearby rivers and channel it down a 6.5 kilometre tunnel
into this huge hall I'm currently standing in, this concrete cathedral around me. This is the Metropolitan Area Outer Underground Discharge Channel, or GCANS for short. Is a water tank. It is an enormous space, 25 metres high. It sits 50 metres beneath the city's streets, 177 metres long and 78 metres wide.
This place cost $2 billion and took 17 years to build. Now it's capable of pumping out 200 tons of water a second.
I cannot describe the feeling of coming down those stairs into this space. Huge columns, the stonework. It is a remarkable space and an astonishing feat of engineering. Now, while the scale of this place might be mind-boggling, here's the thing. The Tokyo Resilience Project is working on doubling the capacity of this system. Whoa! Look at the size of this. So I am currently 50 meters below ground inside what is a new water diversion channel. And the scale of this thing is hard to get your head around. Like, the amount of water that could flow through here is mind-blowing. This space is 12.4 meters wide. It runs for 5.4 kilometers, or at least it will do when they finish building it. And it's going to connect up to 2 other tunnels to create a network that's 13 kilometers long, the biggest of its kind anywhere in Japan.
And it takes some serious engineering to carve out a tunnel of this size. To dig this channel, engineers constructed an enormous TBM weighing in at a massive 2,800 tons.
And this is what that tunnel boring machine looks like. This is the amazing piece of kit that has made this huge tunnel possible. So up ahead of me up here is the massive cutting head that's pushing forward through the soil, 12.5 meters wide, rotating round to dig out this huge hole. You can see here these massive segments. These are being put in to help line the tunnel wall. This amazing machine you can see just up there lifts these segments up, puts them into the newly formed tunnel to form a complete ring, and these hydraulic jacks push off that last ring to push the cutting head forwards to build the next bit of tunnel. Another ring, push forward, another ring, push forward. All that for 6 kilometers. What blows me away when you're walking down it is the scale. How much water are they expecting to flow through here?
But tunnelling through the earth isn't as easy as lifting tunnel pieces into place. To keep the earth on the other side stable, the TBM uses a water mixture known as slurry to balance the pressure of the excavated soil.
で、掘り進めた後はご覧のようにこのセグメントといったものをこちらのですねを掘ったトンネルにどんどん土に貼り付けていって、これを持ってトンネルの力をトンネルのですね土の圧力や水の圧力をこれで受けていくと。
So, what are these 2 pipes? What do they do?
シールドマシンを掘り進める際に冷水といわれる泥水を混ぜてトンネルの先まで送り込んでます。その水圧を持ってトンネルが土の中を掘り進めることができます。また掘り進めた後には土が出ていきますので、その土をこの管を通じて地上に出していくといったその管です。
But it's not just the earth that this TBM's got to contend with. The cutter face is equipped with carbide cutter bits that are 48 times harder than a conventional TBM. That's to enable it to break through into the connecting tunnels, something that's never been attempted before.
こちらのシールドトンネルは鉄筋コンクリートの壁をシールドトンネルで世界で初めて抜いていくといった工事となります。それが非常に難しい工事の中身です。
During a storm, this mega-tunnel is going to prevent flooding by siphoning off up to 1.4 million cubic meters of rainwater from rivers across West Tokyo. As water levels across the city subside, the water in here then gets discharged back into the rivers and flows safely out to sea. Along with GCANs, this is part of a vast network of 28 regulating reservoirs across Tokyo. 7 more facilities like that are being constructed to bring the capacity of the network up to 100 millimeters of rain an hour.
In other words, every hour, this network could pump out more rain than London gets in 2 months. And believe me, it rains in London. So why are such big tunnels like this necessary? And what would life be like in Tokyo if this wasn't here? What would happen?
こちらの施設は洪水対策の河川の施設です。こちらが東京は近年非常に雨が強くなっております。そのためこういった施設がなければこちらの流域に住んでいる皆さんの住宅、それから企業、それから東京は鉄道、地下鉄なども多いので、そういった建物が浸水してしまいます。そうしますと人の命が奪われるだけでなく、都市の機能、世界有数の都市である東京の都市の機能がストップしてしまいます。
Just before midday, on Saturday, the 1st of September 1923, a magnitude 7.9 earthquake struck an area 50 kilometers southeast of Tokyo. Over 142,000 people died and nearly 2 million people were made homeless. In the fires that followed, 33,000 square meters of Tokyo were reduced to ash.
It was the single greatest natural disaster ever to hit Tokyo, and as is the way with natural disasters, there's nothing stopping something like that from happening again.
In 1995, the city of Kobe was devastated by a 6.9 magnitude earthquake.
Hundreds of thousands of residents are left searching for food, for warmth, for loved ones.
And in 2011, the Fukushima nuclear meltdown was triggered by the massive Tohoku earthquake and tsunami. Now, earthquakes are typically measured by the moment magnitude scale, with each level being 10 times more powerful than the previous one. Anything above level 4 poses a threat to property, while a quake above level 9 would release enough energy to power the US for over 2,000 years. Nearly 600 level 4 or higher earthquakes have already struck Japan in 2024 alone, and many are nervously predicting the big one, a once-in-a-century quake that would rival the destructive power of the Great Kanto disaster. There's nothing the authorities can do here to stop this happening, but there is a lot they can do to stop it destroying the city, and that starts with learning how to predict when a quake will strike. I've come back to NIED to see how researchers are learning to prepare Tokyo for earthquakes.
This place is amazing, this campus. It's like a Disneyland park full of amazing engineering labs. Just go into each one and see what they're doing. It's so cool. Wow, look at this. Wow. So this is the giant rock friction apparatus. It's the largest machine of its kind anywhere in the world, and I have never seen anything like it. It is huge. So what this is doing is trying to simulate earthquakes. It's trying to simulate what happens deep below the Earth's surface when an earthquake occurs. So you can see it's got these orange jacks across the top here, are pushing the top rock down onto the bottom rock with incredible force. And you can see this machine's engineered to be really strong to push those two rocks together. And then this huge orange jack on the side here creates a massive lateral force that pushes the bottom rock until it slips against the top rock, mimicking what's happening with tectonic plates deep below the Earth's surface. And what researchers and scientists here are doing is measuring data. You can see these rocks are covered in sensors. They're recording what's happening just before that slip occurs and immediately afterwards, so they can start to begin to predict when earthquakes might occur and warn people in time. So tell me about this amazing machine.
Yeah, this is a machine to simulate earthquake in the laboratory. So we'd like to know what is happening during the earthquake. First of all, we'd like to understand the physics or mechanism of earthquake. And I'd like to find some hint to predict the earthquake.
The Earth's tectonic plates are constantly pushing against each other along fault lines, like the kind that Japan sits on. occasionally those plates slip and the energy released creates an earthquake. Now, exactly where and when that happens is what researchers are using the giant rock friction apparatus to try and find out.
I can see all these sensors on the rocks. They're collecting data about that moment.
In the similar to natural case, the fault doesn't slip at the same time. The part of the fault starts to slip somewhere and it's propagated little by little, and these sensors catch the propagation of slip.
How much do they weigh?
10 tons.
10 tons?
Yes.
And the whole machine you said to me earlier is 200 tons?
200 tons, yes, exactly.
So the data you're collecting from here will start to give you those clues and hints to look for to predict earthquakes and when they might occur. That matters because you can give people more warning that an earthquake's coming, people can get to safety in time.
I hope so, yeah.
What you're doing in this space, in this shed on campus here is really, it could change the world. It could really save a lot of people's lives.
The NIED does more than just measure what happens when an earthquake strikes. This is E-Defense in Hyogo Prefecture, about 400 kilometers from Tokyo. This is the largest earthquake simulator in the world. It shakes a massive plate on 3 axes to simulate the ground conditions when an earthquake occurs, and you can take it up to magnitude 7. It's places like this that have been essential in making Japan a global leader in earthquake engineering. But when it comes to construction, how do you build something that can withstand those enormous forces? Well, I've come to the Murray JP Tower. Completed in 2023, it's Tokyo's first ever super tall skyscraper. This place houses a mix of luxury apartments, offices and retail space. But most importantly, it kind of epitomizes the extreme lengths that engineers in this city go to keep buildings standing and the people in them safe.
5 stories beneath the streets of Tokyo, directly under that super tall skyscraper that's rising above my head, you'll find this. Backup energy generators, a huge water supply fed by an underground well, extensive food supplies, batteries, an amazing series of systems that enable this building to keep running independently should the worst happen in the surrounding city. The extent of the engineering down here is incredible. Even this, a 97-ton generator, is sitting on these special springs, these special pads underneath it, that help isolate it from the rest of the structure so it would be protected from the rest of the building when it started to shake during an earthquake.
These diesel generators work alongside a massive bank of batteries in case of an emergency, so that if a disaster destroys the power grid, the tower can be completely self-sufficient. It's so safe here that the skyscraper acts as a refuge for people in the area. Inside this storeroom are enough supplies to feed 3,600 people for 3 days. These kits include everything from tinned food, bottled water, toilets, and even baby supplies. But none of this would mean anything if the building wasn't still standing in the first place. Part of this tower's earthquake defences are made up of hundreds of pistons known as oil dampers located all around the building. I caught up with Kai Toyama from the structural design team to learn more.
So this is a scaled down model of what we're seeing behind us. We're on level 33, which is here. This is level 34, and this is showing us what happens during an earthquake.
はい、これが柱コラムですけども、地震が起こると建物はこういうふうに揺れます。それとここを見ていただきたいんですけども、動いているのが分かると思います。で、これがオイルの中で動いているということです。で、地震がですね終わると、これ触るとですね、ほんのり暖かくなってます。つまり地震の揺れのエネルギーが熱のエネルギーに変わって建物の揺れが収まっていくということです。
Wow. So this is another feature that helps this building resist earthquakes. What is this? How does it work?
これは粘性体制震壁と呼ばれる制震装置です。で、これの仕組みもまた模型を持ってきたので、それで説明をさせてください。壁、この赤い壁がこの透明な壁と同じです。この赤い壁の中にはドロドロした液体が入っています。で、地震が起こると中の液体が動いているのが分かりますか？非常にネバネバした液体なので、人の力ではとても動かせません。これは地震の力でこのように動いて、先ほどと同じようにだんだん暖かくなります。
Viscous wall dampers like this, how many of them would there be in a building this big?
はい、このビルにはこのタイプのものもやっぱり300機以上あります。300 oil damper and 300 this one.
Wow, across a super tall building. Wow. What blows me away is that this is just behind a cupboard and a corridor. You wouldn't know it was there, but it's a critical feature to keep this building standing. It's amazing.
Currently, the city's evacuation centres can accommodate just over 3 million people. Now, that might seem a lot, but when you consider the size of Tokyo, in the event of a major disaster, those centres could be easily overrun. To avoid that happening, the Tokyo Resilience Project wants to eliminate the need to evacuate in the first place, just like at the Mori JP Tower. This is one of many neighbourhoods in Tokyo with fragile wooden housing which is going to be upgraded. But it doesn't stop there. Bigger apartment buildings like this are also being re-engineered so they can withstand the same level of earthquake as the Mori JP Tower. In fact, when this project is complete, 100% of Tokyo's housing is going to be able to withstand a magnitude 7 quake. In other words, if you're at home and a quake hits, you should just stay where you are. Even if an enormous earthquake strikes, the Resilience Project wants you to carry on with life as normally as possible. But it doesn't stop there. Earthquakes are devastating, and not just because of the loss of life they cause by collapsing buildings. Roads become blocked, hampering relief efforts, utilities burst, and fires spread. When the Great Kanto struck just before noon, thousands of households across the cities were preparing lunch on open stoves in timber homes. The firestorm this created helped make the event the worst disaster in Tokyo's history. Even today, the city isn't immune to these secondary effects. About 86 square kilometers of Tokyo is still densely packed with old wooden housing, which is at high risk of secondary fires. Neighbourhoods like these have been earmarked for redevelopment, which will feature new roads, tall buildings, and parks to act as fire breaks.
And that's not all. Overhead wires and cables like these are prone to collapsing and starting fires. And that's why over 1,000 kilometres of roads across this city are having their overhead utilities replaced and moved underground. That's not only to prevent fires from starting, but also to improve access routes for emergency vehicles. Which brings me to the last thing I've come to see. Konnichiwa. So where are we now? What is this structure?
この永代橋は、関東大震災の時の復興橋梁です。1926年に施工されて、今年齢でいうと98歳です。橋の真ん中が100メートルということで、当時一番最長の橋として架けられました。現在は日本の重要文化財に指定されています。
This is one of over 400 bridges in Tokyo being retrofitted with enhanced earthquake protection. But it's also much more than that. A bridge has stood on this site for more than 300 years, with the previous version destroyed during the Great Kanto earthquake. When this structure opened after that disaster, it was a symbol of Tokyo re-emerging stronger and more resilient than ever. Its re-engineering today represents a renewal of that mission.
はい、地震が発生した時に桁がこっち方向に動こうとしますので、それを抑えるようなシステムになってます。この装置の中にはスプリングが入ってまして、スプリングでエネルギーを吸収するものになってます。こちらのものは橋のちょうど真ん中に設置してますけども、これは強軸直角方向ですね。こっち方向の大きな地震に対して
So these features we're looking at, the ones you just showed me, the ones on the side, they're counteracting the longitudinal force across the bridge, and this one's counteracting the lateral force across the bridge. They work together to protect the bridge as a whole.
はい、その通りです。地震っていうのは縦方向、横方向、どっち方向が来るか分かりませんけども、どの方向から来ても橋が落ちないような、そういうことで補強を行っているところです。
This project is vast, not just because of huge underground reservoirs, but also because of stuff like this. They really have thought of everything, from the biggest megastructures right down to the smallest utility cable. And that is how you protect a city the size of Tokyo from every disaster imaginable. As an engineer, how does it feel to be involved in something as huge, important and consequential as the Tokyo Resilience Project. It touches millions of people's lives. You must be very proud to be a part of it.
やはり、強靭化っていうことで、特に日本というか東京っていうのは地震が多いところです。で、そういうものに対して、都民とか市民の命とか財産を守れる仕事に就けてるっていうのはやっぱり やりがいがありますし、橋梁技術というところで特化したところで仕事ができているのも誇りになってると思ってます。
There's a reason why Tokyo is at the top of so many people's lists of must-visit cities. This place is so exciting, so unique. But it's also a place of contradictions. Just when you think it's chaotic and intense, it then hits you with moments of calmness and serenity. So many people live and work here, but it's so organised, everything works so well. It's the world's biggest city, but it's put incredible attention to detail into this project to protect itself and keep its citizens safe. The Tokyo Resilience Project is like nothing I've covered before. It's so big, so vast, so ambitious. And we've barely scratched the surface of it in this video. I've been lucky enough to travel the world and see so many cities, but I've never seen any as prepared as Tokyo for natural disasters. But I guess other cities don't have to be, you know? London doesn't have to worry about earthquakes. New York doesn't have to worry about volcanoes. Tokyo's got to worry about all of that and more. Through all those disasters over the years, this city has learned. It's brought that learning from more than a century into the Tokyo Resilience Project, and it's constantly adapting and getting ready for what might come next. Because as anyone here will tell you, it's not a case of if disaster might strike, but when.
Maybe you're thinking, that's it, that's the end of Japan's disaster prevention planning. Well, you'd be wrong, and I was obviously setting you up. What if disaster strikes and you're not at ground level? What if you were, say, I don't know, 634 meters above the skyline? This is the view from the Tembo deck. It's a viewing platform at the top of the Tokyo Skytree, a massive observation tower and the third tallest freestanding structure in the world. It offers the kind of incredible views of Tokyo that you'd expect from a viewing platform more than 350 meters in the air. But if that's not high enough for you, you could head up to the Tembo Galleria 100 meters above that. While you're discovering your newfound fear of heights, here's something else for you to think about. Tokyo sits in one of the most seismically active regions in the world. In fact, in Japan, some kind of seismic activity is recorded about once every 5 minutes. In other words, spend long enough here and there's a fair chance you might see an earthquake strike the earth below your feet. But don't expect to feel it, because during a quake, this is one of the safest places to be in the entire city. There's no need to rush for the exit. In fact, you can sit back, grab a coffee, and even enjoy the fine dining. But why? Or more precisely, how? How can this here, at one of the highest viewing platforms in the world, be safe enough to ride out the kind of earthquake that would flatten most cities? You might think it's all down to the Skytree's intricate steelwork, but you'd only be half right. The real answer lies in the kind of ingenious engineering and determination to defy the odds that's made Japan one of the greatest construction superpowers on the planet. If you're building anything of significant height, then one factor is going to dominate your design: the wind. Towers may be thinner than buildings, but the same principle applies. In fact, the most famous tower in the world owes its iconic profile to early breakthroughs in the understanding of wind resistance. The wrought iron of the Eiffel Tower proved a strong and relatively lightweight material and allowed the tower to climb to an unheard of 330 meters. But it had a critical drawback: it flexes. To address this, the tower's engineers used their pioneering understanding of aerodynamics to give the tower its swooping, tapered shape. This channels wind downward from the more vulnerable upper sections to the stronger base, stabilizing the entire structure against the wind. 90 years later, Toronto's CN Tower represented another breakthrough when it became the tallest freestanding structure on Earth. Its propeller-shaped cross-section gives it an enormous strength by reducing the sway caused by wind. This shape is so effective at diffusing wind loads, it's also used for the core of two other giants, the Burj Khalifa and the upcoming Jeddah Tower. But there's a problem. This shape resists wind by providing strength and minimizing sway, but in an earthquake zone, that level of rigidity is actually pretty deadly. Many Japanese buildings have stood the test of time by doing the opposite. This is the pagoda at the Hiroji Temple in Ikaruga. Like everywhere else in Japan, this area experiences regular earthquakes caused by the multiple fault lines that cross this country. Despite that, it's one of the oldest wooden structures in the world, thought to have been built in the year 711, but some parts of the structure date back even further. Pagodas are a common sight in Buddhist temples around the world, but the ones in Japan, known as Goju-no-to, are unique. They typically have 5 stories representing the 5 elements, and it's the ingenious design of the joints between these floors that hold the key to their resilience. The beams are held together in grooves which aren't fixed. When an earthquake strikes, the beams slide against each other, with friction absorbing some of the energy. Making sure the structure maintains its balance is a tall wooden pole known as a shimbashira. In a mark of the incredible longevity of these buildings, the shimbashira in the Hyoji Temple dates back to the year 594. It was in homage to this structure that the Tokyo Skytree nicknamed a crucial part of its earthquake-proof structure. But to understand the root of the Skytree's extraordinary stability, we need to look at its foundations. The tower shares the same triangular cross-section as both the CN Tower and the Burj Khalifa at its base, where it uses that shape's strong profile to really anchor itself to the ground. Each corner of this triangle features a cluster of wall pile foundations driven 50 meters into the earth. Between these is a shallower wall foundation made of reinforced concrete which links and reinforces those 3 points. Rather than single rods, the foundations are made of continuous walls of steel-reinforced concrete, which increases the surface area in contact with the ground. That creates more friction with the earth to counteract the push and pull forces of the tower above during high winds. Above ground, the Sky Tower is made up of 3 main parts. The observation deck sits on top of this enormous lattice. It's a structure made from high-strength steel, twice as strong as your standard steel framework. At the base, these pipes are 2.3 meters wide and 10 centimeters thick. Rising up from there are 3 corner trusses connected by the outer lattice. At the ground level, these align with the foundations, creating a kind of tripod effect, but they become more rounded further up the structure. Inside this is a cylindrical middle section housing the tower's 4 elevator shafts and other utilities, and nested inside that is an enormous concrete pillar, the shimbashira. This huge trunk of reinforced concrete is 375 meters high and 8 meters wide. At its base, the concrete is 40 centimeters thick, but this increases to 60 centimeters near its tip. With some incredible access, I got to crawl into the very heart of the Tokyo Skytree to discover how this feature forms the tower's vibration control system. As an engineer, getting to see something like this up close gave me goosebumps. When an earthquake strikes, the flexible truss structure sways, but because the central concrete pillar, or shimbashira, is structurally separate, it vibrates at a different frequency, allowing it to cancel out some of the vibrations of the outer structure. In addition, the core column is connected to the steel tower by an oil damper to prevent overstroke within the narrow core. That's enough to absorb up to 50% of the forces experienced by the tower during an earthquake. But that's still not enough to keep something like this standing in Tokyo. The final line of defense for the Skytree is a seismic base isolator. Incredibly, this massive concrete core rests on these 6 rubber bases, each 1.4 meters thick. Because the rubber is pliable, it serves as a flexible connection between the core column and the foundation to prevent damage during an earthquake. If an earthquake were to strike now, this would be a perfectly safe position to be in, although it didn't feel like that for me. Sitting down here, all I could really think about was that enormous column of concrete above my head. All put together, these measures give the Skytree an incredible level of earthquake resistance. The structure would still be standing and open for business even if it was the epicenter of a magnitude 7 event. That's the equivalent of 1.8 billion kilograms of explosives being detonated underneath its base. But the Skytree is so safe because it needs to be. Beyond its role as a tourist destination, it also plays a crucial part in Tokyo's disaster planning system. Should the city be struck by a devastating natural disaster, the residents can rely on vital information being broadcast from the mast at the top of this structure. For them to work, they need to remain stable in the strongest earthquake and the strongest wind. Because even though the Tokyo Skytree can withstand ground shakes, it also has to battle the wind just like any other tall building. To keep its precious broadcast antennas safe, the Skytree has 2 remaining tricks up its sleeve. It's tuned mass dampers. Now, tuned mass dampers are a common feature in skyscrapers, like this one over in Taipei 101, and they help reduce the vibrations caused by forces like wind or even earthquakes. They consist of a huge weight that acts as a pendulum. In a similar principle to the pillar and truss structure of the tower, they sway at a different frequency to the surrounding building, absorbing vibrations caused by forces like the wind. The Skytree goes further by using 2 of these devices. The first, at 620 meters, weighs 40 tons, and the second, at 625 meters, weighs 25 tons. Aside from their weight, the 2 dampers are identical in design, consisting of an inverted pendulum supported in its frame by a series of springs and universal joints. They help dampen the wind resonance of the tip of the Skytree, known as the gain tower, and prevent television transmission interference. Now, the gain tower is intentionally designed to be light to reduce the resonant wind speed and prevent transmission interference, but the TMDs improve this performance even further. Tokyo is not an easy place to build. If it's not the constant threat of earthquakes, there's always the threat of floods, typhoons, and even volcanoes that could cover the city in a blanket of ash. And yet, these challenges haven't stopped Tokyo from rising to become one of the most vibrant and advanced cities on the planet. Structures like the Skytree embody the resilience and ingenuity of Tokyo's engineering. In them, we see the true spirit of building, not just to shelter, but to rise above the odds, to create something enduring and extraordinary. Now, if you're afraid of heights, then I'm sorry, because we're going from that massive tower to a mountain. But don't worry, because we're not going to the top of the mountain. Instead, we're going inside it. Something huge is being constructed in a remote corner of Japan. It's costing over $500 million and is the biggest of its kind in the world. It's been in development for over 20 years. It's over 80 meters high and nearly 70 meters wide. But you're not going to spot it very easily, because this enormous structure is hidden deep in the landscape, quite literally. And when it's finished, it'll look something like this. So, just a couple of simple questions. What is it? And why are they hollowing out a mountain to build it? Okay, now before we go any further with this video, we're going to need to do a quick science lesson. So notebooks open and pay attention at the back. Our universe is made up of tiny subatomic particles such as quarks, bosons, and smallest of them all, neutrinos. Neutrinos act in strange ways. They fly through space, but don't interact with any other matter. Billions of them move through your body all the time without having any effect on you at all. Now, if we understood how that happened, it could fundamentally change how we think about the universe. But as you'd probably guess, with the smallest particles in the universe, they're quite hard to spot. One way of detecting them is by smashing larger particles together at high speeds and recording the reaction. That's what's happening over at the Large Hadron Collider in CERN. Another way to observe them is just by listening, which is about as easy as it sounds. Ideally, you need somewhere remote, quiet, and very peaceful. Fortunately, Japan is pretty good at that. This is Kamioka, a small town in the Japanese Alps, and this is Mount Nijugo, home to the Hyper-Kamiokande. It's a $600 million science experiment led by the University of Tokyo and supported by researchers from 21 countries. When complete, it'll be the largest neutrino observatory in the world, and a breathtaking feat for Japan's construction industry. But as incredible as it is, it's actually not the first of its kind. This is going to be the third Kamiokande in this region. This part of Japan is known for its zinc mining industry, and it was the expertise of a local mining company which, back in 1983, helped construct the first Kamioka nuclear decay experiment, or Kamiokande for short. The success of that gave rise to the Super Kamiokande in 1996, and the Hyper-Kamiokande under construction today. It consists of a huge cylinder carved into mountain rock and accessed by an approach tunnel at the top and a secondary tunnel at the base. It's 88 metres high and 69 metres wide. That's big enough to fit an entire Boeing 747 standing on its end. Now, don't worry, we're going to get on to how it works later, but first off, how do you build something like this in the middle of a mountain? Well, plans for the Hyper-Kamiokande go back to 1999. Then, after more than 2 decades of development, work began in May 2021 on the access tunnel. Using a drill and blast technique, it took just 9 months to excavate the 2-kilometre approach tunnel, which was then sprayed with concrete to create a smoother and more stable surface. This approach tunnel leads to the centre of what's going to become the roof of the observatory. Now, as the observatory sits 681 metres below the mountain peak, a dome structure was created, which was then reinforced by a steel truss to hold the enormous weight of all the rock above it. That was completed in October 2023, and now the team have begun the next stage of the project, blasting down through 71 metres of rock to create the enormous cavern the observatory is going to sit in. This rock is hard work for the construction crews, but it's what makes this site perfect for spotting neutrinos. The density of the rock is the equivalent of this observatory sitting 1.7 kilometers below the surface of the ocean. That's no problem for the neutrinos, which can pass through entire planets with ease, but it provides excellent insulation from cosmic rays and other background radiation which could ruin this experiment. Drilling's due to complete in 2025, but at that point there's still going to be a long way to go before it can detect a single subatomic particle. First, the inside of the cavern's going to be lined with 2 layers of concrete and, crucially, a waterproof layer. That's because this cavern is set to become the largest tank of water in the world. Once fully watertight, 260 million litres of water are going to be pumped into this enormous cavern. That's nearly 4.5 times larger than the world's largest aquarium over at SeaWorld Abu Dhabi. It's going to be flooded from the water table in the mountain and will take about half a year to fill. But as clean as this water is, it undergoes further treatment with UV light and other means to create water so pure it's capable of dissolving metal. Now, the massive tank of water creates the perfect conditions to spot neutrinos in. Time for a bit more science. When neutrinos pass through the tank, occasionally they'll collide with electrons, giving off a weak glow known as Cherenkov radiation. And that is what this whole thing is being constructed to observe. Tiny glimmers of light in a giant cavern full of water. The Hyper-Kamiokande isn't complete yet, but to get an idea of how it will look, here's its smaller sibling, the Super Kamiokande, which is less than half the size. Here, the cavern's been drained because engineers are performing maintenance on these photodetectors, the thousands of light sensors that together act as a giant camera. The ones in Hyper-Kamiokande are so sensitive that a single sensor could detect the light of a torch being used on the moon. Together, they act as a giant camera that picks out the faint traces of shrink-off radiation created by reacting electrons. 40,000 of these are being manufactured for the Hyper-Kamiokande, each one almost twice as sensitive as their predecessors, and specially designed to withstand the enormous weight of 260,000 tons of water. Construction is expected to fully complete in 2026, and the Hyper-Kamiokande should start detecting neutrinos and performing other experiments by 2027. Now, as cool as all of this is, you might be forgiven for thinking, so what? After all, what has particle physics ever done for me?
What have the Romans ever done for us?
Well, for a starter, if you've ever had a medical scan or had a tumour diagnosed, you have particle physics to thank for that, as well as treatments for everything from cancer to AIDS. It's led to greater understanding of fluid dynamics, which helps in the construction of long-distance pipelines and gives us more accurate weather forecasts. And let's not forget that it was for a group of particle physicists that Tim Berners-Lee developed a new system for quickly and efficiently sharing information. A system which is enabling you to watch this video right now. It's probably pretty fair to say that this is one science experiment that's definitely going to live up to the hype.
Now, we've answered a lot of really important questions so far, like how can a mega build protect a massive city? How do you construct something 600 meters above ground? And how do you construct something 600 meters below ground? But next, we've got a really, really important burning question. What happens to Japan's buildings and infrastructure if they get really, really wet?
Imagine a storm so powerful it can wash away roads, destroy an entire neighborhood, or even collapse a mountain. Now imagine taking that terrifying power of nature and being able to control it with the push of a button. That's what happens here, inside this building in Japan. So what is it, how was it built, and how was I talked into going for a walk in the rainiest place on Earth?
It is what it is. Okay. Did you get that? So here we are, we're at the large-scale rainfall simulator just outside Tokyo in Japan. Large scale is a good way of putting it because it is absolutely enormous. It's like an aircraft hangar, much bigger than I was expecting. To be quite honest, I've been dreading this moment. I've been building up to today. What the production team have told me is that the US Geological Survey say that 8 millimeters of rainfall an hour is classified as heavy rain, and that the machine behind me can go up to 300 millimeters an hour, which isn't necessary, it's not natural. I don't need to put in that kind of scenario, but for your viewing pleasure, we're doing it. So here we go. I've brought my umbrella, which is one of these lovely clear Japanese umbrellas, but not sure it's going to be enough.
Just before the ritual humiliation, let's actually do some work. Before we get to know how this place was built and why it's necessary, we need to discuss the strange quirk of Japanese housing. What you're looking at here is a typical Japanese house. Now, while the major cities are dominated by those mid and high-rise apartment blocks, it's houses like these that you're going to find in towns, villages and suburbs right across the country. If you're thinking of moving to Japan and you want to find a bargain, it's a house like this you'll want, and the older the better. That's because, unlike basically every other country on Earth, housing in Japan loses value over time. After about 30 years, houses like these are going to be knocked down and replaced by a newer model. But why? Well, close your eyes and picture the Japanese countryside. Maybe you're imagining lush mountains and valleys, steaming hot springs and ancient temples, a place that reflects a deep-rooted connection with nature. And you'd be right, but that connection isn't always as peaceful as it seems. Japan only exists because of nature's raw power. It was forged when massive tectonic forces pushed it out of the sea millions of years ago. It gives this nation a stunning landscape, but it's also made it the most earthquake-prone country on the planet. Japan faces some of the world's most violent storms. Typhoons regularly sweep through, bringing torrential rain, devastating floods, and powerful winds that can tear rooftops apart. As if all of that wasn't enough, with over 80% of Japan covered in mountains, those torrential storms bring another very real threat: landslides. Even if your house survives an earthquake, it could easily be swept away in a river of mud and rock. It's largely because of all this that the idea of impermanence, that nothing lasts forever, has been really ingrained in Japanese culture, even in something as solid as a house. It's why many homes are built with semi-permanent prefabricated designs, not as a sign of weakness, but as a smart, pragmatic response to an unpredictable landscape. But that's only half the response. The other half is world-leading research into flood-proof urban planning and landslide prediction technology. This is Tsukuba. It sits 75 kilometers northeast of Tokyo and has a very good claim to be in the scientific center of Japan. It's home to both the Japanese Space Agency and the headquarters of the snappily named National Research Institute for Earth Science and Disaster Prevention, which they helpfully shorten to NIED. Now, we came here when we were making our epic documentary about Tokyo's disaster resilience infrastructure, and we just couldn't leave without seeing inside this building.
This building established in 1974, and this is a big typhoon is coming in the damage affected in Japan. Now we are research on the mechanism on flooding and the landslide using this facility.
There are simulators like these around the world, but none match the size or sheer power of this place. As I mentioned, the US Geological Survey classifies very heavy rain as ranging from 8 to 10 millimeters per hour. But here, that's not even the first rung on the ladder.
In system is 50 millimeter per hour to 300 millimeter per hour. This is very wide range.
300 millimeters an hour is just shy of the strongest rainfall ever recorded back in 1947.
But we do begin tonight with this Category 4 hurricane slamming into the U.S.
To put that into context, when the devastating Hurricane Ida hit the US back in 2021, the maximum rainfall recorded in one day was just 200 millimeters. We're going to get to why on earth it's necessary to reproduce such torrential conditions shortly, but first off, a bit about how this place works. The simulator consists of a huge 75 by 15 meter hangar. This suspends a latticework of thousands of pipes and nozzles 16 meters above the ground, high enough for the droplets to reach terminal velocity. These are connected to a pipe on the outside of the building, which feeds water in from an underground reservoir. Running along the outside of the test area is a series of drains which collects the water and stops flooding. This test space is used to trial everything from homes to self-driving cars. For tests on soil erosion and landslides, other areas of the site have permanent facilities set up where experiments can be constructed. But hold on, how do you carry out tests in different areas? Well, as if this building wasn't impressive enough already, get this.
It moves.
The building is a movable system. You can see the rail, long rail, 400 over rail in the left side. This building is moving by electric motor, each wheel.
This vast building effectively works as a self-powered railway carriage, moving at a speed of about 1 meter a minute.
This is over 3,000 square meter in the rainfall area. It's very, very big.
So how does all this relate to housing in Japan? Well, landslides are very common here. They're also deadly, responsible for around half the fatalities and missing people in natural disasters. Japan's Met Office issues warnings to help people evacuate their homes and workplaces before the worst happens. But because landslides occur so quickly, it's a constant challenge to be able to warn people in time. That's where the work of Dr. Sakai comes in.
Now our research aim is resilience for the people. We are developing a sensor for the slope condition. Sensor data is checking the safe or not. It is very important using the facility testing.
What makes the research here so unique is the scale of the experiments undertaken. Tests like this give researchers like Dr. Sakai much more reliable insights than smaller scale projects. But it's not just the size of the experiments here that make this place unique. Being able to reproduce a variety of rain conditions involves more than just cranking up the power.
This system is like a natural rainfall condition, and this natural rainfall state is rainfall drop size, and rainfall speed, and intensity.
It's being able to control the droplet size, speed and intensity that makes this simulator so unique. It sprays water from 2,176 nozzles of 4 different types that can reproduce raindrops from 0.1 to 8 millimeters in size. The bigger the size of the droplet, the faster it falls, and the height of the nozzles helps distribute the rain over an equal area. Discovering more about the science of what causes mountains to collapse is only part of the research that goes on here to help save lives and property. This is an experiment by Ichio Koteman and NIED to develop the world's first flood-proof house. Now, flooding is usually impossible to stop in a house because there are so many entry points, but this house was fitted with a series of countermeasures to stop it from filling up. The windows were sealed with a hollow gasket similar to that used on car doors. The air vents are fitted with a float valve which blocks the water coming in through the airway. Utility pipes entering the building are also insulated by a backflow prevention valve which allows rainwater to leave but not enter the property. It's an incredible development that just wouldn't have been possible without this facility. If you enjoyed this video and you want to get more from the definitive video... Oh no, okay, I can't sign off yet. They want to put this bit in, so here you go guys. Here's a couple of minutes of me getting wet.
Now, I'm not really sure what the dress code is for a large-scale rainfall simulator, to be quite honest, but I've sort of just worn stuff that can get wet. And then they give me these wellies, which makes it look like I've walked out the village, people. I hate you so much right now. Oh, here we go. The moment has arrived. What is coming out of there? This is unreal. I'm on £2 umbrella. Do me proud. Oh God. Here we go. It's a bit much for light rain. It's absolutely hammering it down. Oh my God. Good Lord. The stuff I do for YouTube. I want a little island of dry now. This is light rain.
Right.
This is light rain.
Right.
I mean, he's just told me that's light rain, which blows my mind because I wouldn't think it could rain more than that. But it's about to, apparently. Hey, it's a good ad for the $2 umbrella, right? Mic off, yeah?
Yeah.
You enjoyed that. I'm now absolutely soaked. I've never seen rain like it. It's completely unnecessary, completely unnatural. But yeah, there you go. I'm absolutely soaked to the bone. Well, I didn't enjoy that video. But if you enjoyed that video and you want to get more from the definitive video channel for construction, from the channel that puts me in some of the wettest places imaginable where you sit in the dry and watch, hit that subscribe button.
I know you're all commenting right now about my choice of outfit, but I'm standing by it. It was a practical decision. In fact, let's move on. Let's move on really quickly. And how better to move quickly in Japan?
This is one of Japan's most famous inventions, the bullet train.
Japan's Super Express, the Shinkansen.
But if you think these can go quick, you ain't seen nothing yet.
For the past decade, Japan's been hard at work on the next evolution of these bullet trains, maglev. Short for magnetic levitation, these new trains do away with wheels and levitate down specially made tracks at speeds that can reach 603 kilometers an hour. That's much faster than the current bullet trains, which move at around 210 to 320 kilometers an hour. The trip between Tokyo and Nagoya will take only 40 minutes. That's faster than flying between the two cities, or taking the current 1.5-hour trip on the Tokaido line. The route was supposed to open in 2027, just 2 years' time, but that's not so likely to happen anymore. It's all been pushed back until at least 2034, and all because of one man, Shizuoka Governor Hyper-Kamiokande. This politician has successfully protested against the trains and delayed them by decades. But why would anyone be against maglev? And now that Kawakatsu has been ousted from office, are things finally getting back on track?
The first Shinkansen trains opened in 1964 and transformed travel from Tokyo to Osaka, taking it down from 7 hours to just 2.5. Now, that journey could be slashed again down to just 67 minutes, thanks to advancements in magnetic levitation, or maglev.
It's part of two new lines that Japan is building. The first from Tokyo to Nagoya, then from Nagoya to Osaka. Part of what will make these lines so impossibly fast is that they use that magnetic levitation technology. It's actually pretty old, but has been updated for the 21st century. When this project is complete, it'll have the power to drastically transform Japan again. You see, this isn't the first time that Japan's course has been altered by superfast trains. When the first bullet train debuted in 1964, the Tokyo Shinkansen, the rest of the world was focused on the booming aviation industry. Locomotives seemed like a relic from the past. And yet, Japan doubled down. In 1964, the Shinkansen operated at a top speed of 210 kilometers an hour, far outpacing traditional trains, which moved at speeds below 150 kilometers an hour. These new vehicles had a sleek, streamlined shape which minimized air resistance. It made for faster and more stable travel. Unlike more traditional trains with a single locomotive, Shinkansen were powered by multiple electric motors. Japan put their special new trains on their own dedicated tracks designed for high-speed travel. That meant they wouldn't be stuck behind slower passenger and freight trains. The high-speed tracks were engineered with minimal curves or gradients. That enabled faster speeds to be maintained without the need for frequent deceleration. The Tokyo Shinkansen slashed travel times between major cities. The journey from Tokyo to Osaka, for example, went from 6 hours to just 4. For the first time in Japan's history, rural areas and urban centres could easily trade goods, services and labour like never before. That in turn created thousands of jobs and spurred even more infrastructure developments. Companies could access larger markets, and the country expanded and rebounded from World War II in what was later dubbed the Japanese economic miracle. Starting with that 515-kilometre Tokyo Shinkansen in 1964, the network expanded to consist of 2,951 kilometres of lines with maximum speeds of 260 to even 320 kilometres an hour. Japan has exported its technology across the globe and is rightly considered a leader in high-speed rail. Europe, and to some extent America, are trying to follow in the country's footsteps, using rail to reinvigorate their economies. Just across the sea from Japan, China has also emerged as another world leader in high-speed rail with the largest network on the planet. But it was Japan that was ahead of the curve. Today, its bullet trains are considered part of the best high-speed rail network in the world. An accolade it earns thanks to a combination of unparalleled technological innovation, safety, efficiency, reliability, and great passenger experience. It comes as no surprise then that the rest of the world is eagerly awaiting the next big innovation in Japanese transportation, and the country has some very big ideas. Enter maglev. Now, the concept for maglev trains has actually been around since the 1960s, but what Japan has done is modernise it with superconducting magnets, and they do two things: lift the train carriage off the rails and propel it forward.
But let's look at how that works in a little bit more detail. Maglev technology relies on magnetic forces to lift, propel, and guide the train. It uses the two fundamentals of magnets that we all know: the fact that the same poles repel each other and opposite poles will attract each other. At full speed, the Chūō Shinkansen trains will move at 500 km an hour, although a 2015 test run saw they could reach a world record speed of 603 km an hour. Now, it's pretty widely agreed that those kinds of speeds are basically impossible for a conventional bullet train to hit, and that's because of the friction that's created by their wheels. To solve that problem, Japanese engineers actually looked back in time to a technology that's been around since the early 1900s: magnetic levitation. The Central Japan Railway Company has modernised this tech using superconducting magnets. Basically, electromagnets are cooled to minus 269 degrees Celsius, allowing trains to levitate higher above the tracks. But the trains need to be moving at speed before these magnets come in. So once the train reaches 150 km an hour using conventional methods, maglev kicks in and the carriage is lifted off its rubber wheels. The train then interacts with a set of coils in the track, one used to levitate its mass and the other to propel it forward. Now, without the wheel, the carriages can travel at incredible speeds. The trains are also completely autonomous, controlled by the track rather than the driver, a measure that it's claimed will hopefully make collisions or accidents far less likely. There are other benefits too. Because there are no wheels, these trains can run in almost any weather condition, and it costs less to maintain them. Like the original Shinkansen bullet trains of the 1960s, these maglev trains actually need their own specially built rail lines to minimise turns and to avoid any slower, older trains that may be in front of them. And those new lines don't come cheap. The total cost of the new maglev routes is going to end up at more than $64 billion. Now, back in 2009, maglev was approved and began construction. Everything was on track for the 2027 opening. But of course, that's now not going to happen. The first line is not expected to open until at least 2034, and that second route to Osaka isn't going to happen before 2037. That's an enormous decade-long delay, and it's all because of this small section. Of the entire 287-kilometre maglev route, just 9 kilometres runs through the northern region of the Shizuoka prefecture. Here, the tunnels are going to dig under the southern Japanese Alps. Now, Shizuoka Governor Hyper-Kamiokande has long protested this part of the line for a number of reasons, but his primary issue is to do with this river, the Oi, and it's very important. Not only does it play a key role in the region's culture and history, defining borders and establishing cities from centuries ago, but it's also a vital water source for the prefecture's agricultural activities, primarily the production of tea. The region kicks out an incredible 25,200 tonnes of tea, which accounts for about 36% of Japan's total output, making it the tea capital of the country. But the competition is stiff. There are fears that the construction of these tunnels will alter the volume of water flowing into the Oi River and affect tea production. The river also flows through several hydro-energy producing dams. If the amount of water in the river is lowered, it could affect the region's energy supply. Basically, tinkering with this river could have pretty disastrous consequences for this region across the board. Now, the Central Japan Railway Company promised to pump water back into the river, but their own reports speculate it would still lose about 2 metric tonnes per second. On top of this, Shizuoka is one of the few prefectures that doesn't really stand to gain anything from the new maglev lines. It's the only prefecture along the route without a station, and with the region already suffering from over-tourism, they hardly want more people coming to visit. The government is currently trying to add access fees to their Mount Fuji trailheads in an attempt to curb numbers, which have become unsustainable. In March 2024, JR Central said they wouldn't be able to meet their 2027 deadline because this part of the railway was being held up. That had knock-on effects for the rest of the line and made it unclear when the second phase would open. JR Central and Kawakatsu basically found themselves at a stalemate. At least until a few days later in April 2024. Kawakatsu was recorded praising his staff for being smarter than people who sell vegetables or raise cows. That's not a wise thing to say when your constituency is famed for its agricultural output and you've made it part of your political brand to stand on the side of farmers. Kawakatsu's downfall was swift. Just one day later, he was forced to resign because of the enormous public outrage. In September, the new government granted JR Central permission to conduct a boring survey in preparation for the construction of the tunnel, a dramatic change in position. But while this is a sign that construction could commence soon, the delays are far from over. Other parts of the line have faced their own issues. Soft ground in the Aichi Prefecture has delayed the completion of a tunnel by more than 5 years to the end of January 2030, again having further knock-on effects. All told, there really is too much at stake for this line not to happen. But it's a reminder that so many megaprojects can face delays. The rest of the world is waiting with anticipation to see how Japan might pull this off, and whether they too could adapt this for their own nations. China has even announced its own maglev line in Hunan province. It'd be their first intercity route and could ignite a maglev race between the two countries. Until then, the maglev-enabled future may be some decades away. For now, a simple bullet train will have to suffice.
Do you guys remember when we watched that 100-year disaster mega plan video together earlier on? Oh, that was so nice. To close things out, here is one of my favourite Japanese disaster prevention projects that some of our most serious fans might just remember. This is one of the most important pieces of concrete in Japan, and it's born out of one of history's most chilling events.
This is what it looks like when a wave of unfathomable size crashes on thousands of lives.
And it looks like the tsunami has engulfed several cities.
We are now going into uncharted territory. We are thinking the unthinkable. This could be a Chernobyl in the making.
The 2011 earthquake and tsunami on the east coast of Japan left roughly 20,000 people dead, decimating entire towns and triggering a nuclear disaster. In the wake of the destruction, the government poured billions of dollars into building new tsunami defense systems. Now, nearly 400 kilometers of tall concrete walls are standing along the coast, designed to weaken strong waves and buy people time to evacuate during the next disaster. But the question is, at what cost? Seawalls have long been part of Japan's coastline, and over the centuries the country's made a name for itself as a world leader in coastal engineering. Just take the town of Tōrō. It endured 2 devastating hurricanes in 1896 and 1933. Soon after, it became a global example of coastal defence systems, constructing an X-shaped structure with 2.4 kilometres of seawalls standing 10 metres tall. Elsewhere in Japan, cities were incorporating similar elements of coastal defence, including earthquake-resistant building codes and tsunami evacuation routes. But on March 11th, 2011, they weren't enough.
The villagers had complete faith in this tsunami wall, and they believed it would stop any tsunami. But it didn't.
Japan's seawalls were designed to hold back waves up to 8 metres, but the 2011 earthquake saw them reach 12 to 15 metres in height. The walls did reduce the force of the tsunami, but the massive waves still crashed over the top, in some cases crushing the structures completely and failing to protect the Fukushima nuclear plant.
Really, before that, they were the best prepared nation in the world for a tsunami. But the tsunami simply, to put it simply, was much bigger than they expected.
That's Dr. David McGovern. He's an expert on tsunamis and fluid mechanics.
The approach now is, well, that's fine. We're going to build big walls. We're going to build them in such a way that if they get overtopped, they don't fail as in any other structural way.
After 2011, the Japanese government set aside $12 billion to repair and build nearly 400 kilometers of seawalls along the northeast coast. These new structures are taller than the ones that stood before, rising up to 14.7 meters in some areas, supported by foundations that are around 25 meters deep in places. They come complete with wider bases and reinforced inner walls to better absorb the impact of waves and help prevent them from collapsing. As part of Dr. McGovern's research, he built a massive indoor tsunami simulator in collaboration with HR Wallingford and UCL. It can replicate waves like the ones that hit Japan in 2011.
In terms of sea walls, what's quite key is that when the tsunami approaches, it does so in a way that is not really reflective of how we sort of see it in terms of the movies and films, where you have a great big breaking, crashing wave coming onto the wall. It doesn't really happen like that. And if you were to look at YouTube video of Japan, you would see a lot of the tsunami and the way it kind of comes on to the ground and overtops seawalls. It's not really a broken wave. It's like a continually rising flood. And so when that tsunami hits the wall, it tends to do so in an unbroken form. And that means that the force on the wall really is just described by this hydrostatic force.
New recommendations in Japan's key disaster scenario manual include using geotextile membranes in sea dikes to try and stop the leaking of infill material, widening breakwater rubble mounds, and interlinking and reinforcing concrete blocks in seawalls. But the wall's height is the biggest upgrade, and perhaps the biggest downside. One concern researchers have is that super high seawalls could actually make the impact of tsunamis worse by creating a dam-like blockade that could release an even more intense torrent if it breaks. And to some residents, they're simply an eyesore. In some areas, they're nearly 4 stories high, blocking the view of the sea entirely and leaving some locals feeling like they're in a bit of a prison. Others worry that the walls will put off tourists, or that they're destroying their community's livelihood and culture next to the sea.
I think the main takeaway is that this is a natural hazard, and it's not one that we're ever going to be able to defend against completely.
Not all tsunamis are created equal. Level 1 tsunamis come every 50 to 160 years, and they're what the new seawalls are designed to protect against. But for level 2 tsunamis that can occur every few hundred or few thousand years, seawalls alone aren't enough. Public education, evacuation routes, and adequate warning systems all need to form part of a wider system of defence. Some have suggested alternatives or supplements to the towering concrete walls. One idea is tsunami mitigation parks, essentially combining green elements like hills and trees with the more traditional grey concrete engineering bits. The Merino project proposes building concrete breakwaters on the coast, backed up by deep-rooted trees to help weaken the power of tsunami waves and stop drifting objects. Of course, another tactic is to move further upland away from the coast. Many municipalities have already relocated their public facilities to higher ground, and some have banned construction on flatlands near the coast. Japan's seawalls are an astounding feat of engineering and offer a degree of resilience in the face of devastating destruction. But they also highlight the delicate balance between protecting ourselves from nature while living alongside it, something that's becoming even more prevalent as extreme weather becomes more common.
So there's 2 things that need to be done. The current infrastructure, which is tens of billions of pounds worth of infrastructure around the world, needs to be looked at to see whether it's going to be fit for purpose or whether it needs to be retrofitted. And then any new infrastructure, which we will need a lot more of because of the increased storms severity and frequency, and because of the sea level rise, how do we design that with that in mind? And the big question is we still don't really know precisely what the future will hold.
The 2011 disaster showed us that even the most tsunami-proof cities aren't indestructible. 10 years later, this massive stretch of towering concrete stands as a constant reminder of the past. and a bid to engineer safer towns for the future.
That's it. Japan, we love you. Keep making these insane projects, and I will keep making the insane 15-hour flight over there to document them. And if you're still watching, then I love you too. Let me know which one of these videos was your favorite down in the comments. Mine was the one where I didn't need an umbrella.